All right. Okay, so the the only quiz that we have was due last week, and so everybody's finished with it. And you guys are able to see Moodle here, right?
Yes.
Yep.
Can you see the dihydrogen monoxide website now?
Yes.
Okay. I wasn't sure if it would let me switch between tabs, but I guess I can. So, sadly, most of you had to use a PDF version of this because the website was down, but now it's back up. Um, so, well, before I do that, I'm gonna stop sharing this and I'll share this thing here. I'll go over here. So I don't know, I can't remember exactly what everybody's answers were, but so DHMO, dihydrogen monoxide, di meaning two, hydrogen meaning eight, mono meaning one, oxide meaning O, and you end up with water. 77% of the students in this class wanted to ban water.
Wow.
It's pretty right on par. Usually it's somewhere between 65 and 80. So first off, let me ask, what was the purpose of this? What do you think?
To teach us to learn the chemicals before jumping to conclusions.
Sure, I don't mind that answer at all. I think
Don't believe every scare tactic out there.
not even every scare tactic, just like don't believe everything you read just because you're seeing it on the internet. Just because somebody posted something on your Facebook page, those of you who are watching this recording or any of you who did say that you wanted to ban it, you need to think about that. The next time you see something and you're reading something on social media or even in the news, you need to look into it before you make a decision. That's just one source of information. This is one source of information. So why do you think people were ready to ban water?
Because the way that the article wrote it, it's made it sound dangerous and yeah.
It absolutely is dangerous though, right? I mean, unless you're
It
Aquaman, you're not, I mean, you might not be scared of the water, but you definitely have respect for it.
Yeah, it's like you take too much water and you can get water poisoning.
Absolutely. Water poisoning is a thing. Doesn't happen very often, but it absolutely has happened. Everything is a poison if taken in the correct dosage. So, why did the person who came up with this, what is up with this graphic here in the upper left-hand corner?
No idea.
It looks like a sunflower.
Okay. How about so here's the Environmental Protection Agency. Look at their logo.
They made it look similar while not making it look
Identical.
exactly the same.
You got it. Nailed it. So what he did is he just went and did as much as he possibly can. I mean, this sounds official, right? The United States Environmental Assessment Center. He has the United States and Environmental Assessment Center segregated from each other because you can actually be nailed for, say, if there was no line there and that was all one thing, then somebody could come in and say, you can't say that. Like US Bank, they would never let that be a name of a corporation anymore because they don't want people to think, like when people come to this country, sometimes they think that US Bank is the Bank of the United States, which is not, obviously, that's the Fed. But so the name of the country isn't allowed to be used in businesses anymore. So all of this makes a little sense. How about the fact that it's an ORG ending?
.org makes it sound a bit more official.
I agree. It used to be a little bit official when websites first came out, but at this point, there are only a few website URL extensions that are controlled. One is edu, which is why if you can enter a valid edu email address into like Apple's website, they'll give you a discount on buying a laptop or something like that. Same thing with Microsoft's site. And the gov websites, those guys are all controlled. And anytime you see like a complex one for a government agency, like Hood River County is like co dot hoodriver dash or hood dash river dot or dot us, like those are all regulated. You would have to show cause to get one of those extensions, but all the rest of them are open. Anybody can get them as long as they get them first. Did you find anything on this website that's incorrect?
We didn't have the website available. We had a PDF.
Sorry, did you find anything in the PDF? Was just a printout of the website? Was anything in there like wrong or a lie?
I would say talking to certain professionals about the dangers.
Okay, overemphasizing the fact that it's more dangerous than it is, but how about, I mean, you're okay with this one, right?
Yeah, drowning.
Drowning. How about this one?
Kind of like how your skin gets pruning.
Yeah, the wrinkly fingers.
No, this is the solid form of dihydrogen monoxide.
Ice, yeah.
Oh,
So
Frostbite.
frostbite.
yeah.
This one here?
Like coughing, choking, puking.
No.
all that
In,
stuff.
how about I gotta go, I have to go pee a lot.
Yeah.
How about this?
The
Yeah.
rain.
Yeah, it's the rain part of the acid rain. Steam burns, certainly. Soil erosion, well, we live in the gorge. The gorge is there because of soil erosion. Wet roads, right? Decrease effectiveness of braking. Is it going to be found in the biopsies of precancerous tumors? Yeah, it's water. Vicious dog attacks? Yeah, it's water. What about these ones down here? In this list, what is this person who came up with this website trying to do?
Scare.
But more than just scare, he's trying to be very broad in his scare tactics. He's trying to find something in here that scares you personally. So maybe you don't really care that Olympic athletes use performance enhancing drugs, but maybe you do care about Scientology or something. Like somebody in your family's in Scientology and you think it's a bad thing, so he put that in there. Or
There's a reference to the Triple K.
oh yeah, so here's KKK. So if you're a white supremacist or hate white supremacy, then you can talk about that, or the NCAACP, which is the same thing on the opposite side. Obviously, Hitler death camps, probably not something that most people, although some people are still okay with.
The waterboarding.
Waterboarding, sure, absolutely. It's used by terrorist organizations. Well, indirectly, of course it is. We use it in community swimming pools. Yeah, it's the pool part. So really, he's simply trying to find something that upsets you, and then once that happens, then most people can't reason through what's going on, and they just accept what it's being said and move on from that. So the major problem with this is people making decisions on subjects or decisions that they make when their information was purposely false, or they just didn't understand the information. The real reason behind this is for a person to understand that just because I don't know what dihydrogen monoxide is and I can't figure out what the name actually means, that, I mean, if you did one Google search on DHMO, you get 1 million sites that say, don't get tricked into this.
You get that actual website.
Oh, yeah, absolutely.
That exact website pops up as a parody.
You're right. This website pops up, but then you also get a bunch of websites that say, don't fall for this trick.
Yeah.
But most people don't bother reading those. They'll read the first one and it comes back to this one and they're like, oh, he gave us this website and Google, this is the first thing that pops up in Google, so it must be official. That's not how citing a correct source works. Nowhere in here does it talk about where this person is from, where the information is from. You can't find any corroboration with anything else. When if you ever get to meet one of your state or federal representatives, like a Greg Walden or a Jeff Merkley or somebody like that, don't ask them about this, but ask one of their staff members, how many letters do you get about dihydrogen monoxide? And they'll tell you that they've got a little file in the office for their special constituents who make mistakes about stuff like this and other things. Sadly, that's used to be not as big a deal, but since the anti-vax movement has come out, it's become a serious issue since those people are actually endangering the lives of people who can't get vaccines. So, did you guys, anybody look up where this came from? This whole concept of dihydrogen monoxide?
I know it's been used in pranks in some campuses.
Certainly. It was a 14-year-old kid. He did it was, I think, his 8th grade class. Yeah, so it was like a middle school class. They were talking about naming compounds, and he went home and was talking to his parents about it, and he realized they didn't know what he was talking about at all. And so you remember those science fair boards? They're like a trifold, like set it down at a table with a bunch of stuff stuck to it, and then you talk about a topic.
Yep.
He did one of those for dihydrogen monoxide. The only people that knew were the principal, his teacher. I think that was it. The newspaper came in. They did a story on it the next day. And what his focus was is it was a small community in Idaho where the town's economy was basically around the sawmill. And he had lots of things like the sawmill is dumping dihydrogen monoxide into our river, dumping water into the water. And he asked the question, should we be doing something about this? So the community got really upset, and it was only in the paper for a single day. And the mill was very confused about what was going on. And people were actually talking about doing something to shut the mill's ability to dump water back into the water. If that mill had shut down, the entire town would disappear. But people were still ready to jump off this. And so the next day they wrote a retraction saying, yes, this was just a kid's joke. And that story was about water and we took it too far and whatnot. He obviously won his little fair. But this thing turned into a phenomenon called Zionism, which was this kid's last name. And so this is being able to fool somebody into thinking something is like has certain properties when in reality it has completely different properties. Yeah, that's probably about it with that. So I definitely don't want anybody making mistakes like this. And what you need to do is, after you read something, is go find some proof, go find some backup, find a bunch of other sources that are legitimate that back up that. There's like a meme running around on the internet talking about this person says, hey, I'm a new anti-vaxxer and I'm trying to find a peer-reviewed journal article that backs up my thinking, and I'm having trouble finding that. Well, that's probably because it doesn't exist, because it's not a real thing. So make sure that when you do finding the information to back up your argument or your side of a topic, that you can use sources that are legitimate.
It's like the anti-vax movement is so stupid. It's like not even a pure Amish community is anti-vax. It's like they get vaccinations too.
Well, they don't want to die.
Yeah.
Their lifestyle is interesting, but they understand that if things aren't going well, you can go someplace else and get help. Like if a woman needs a C-section, they will go to the hospital and get a C-section. They're not completely shut off from the world just because they don't agree with what's going on. And sometimes I think it would be really great to not have all the things to distract you, and you can just go about your life and hang out with your family. But and that's really all it is. And I lived near them when I lived in Pennsylvania, so I met lots of them, and I respect
It's
their.
like, I just truly find it funny. It's like the Amish have more common sense than these anti-vaxxers.
Well, their ability to buy into the technology when they don't use technology should really let people realize that it must be a decent thing, or they would totally stay away from it. And it actually, I mean, it absolutely is a technology. Technology usually think about something electronic or mechanical, but that's not actually what the definition of technology is.
Yeah, straying from this class, like even a few Amish communities, like if it's allowed within the charters, like some of them even use certain motorized vehicles or generators for their farms and stuff.
Sure. Yeah, the other group that's closely related to them that broke off are called Mennonites, and they're kind of like Amish, except they'll use cars, but the car can't be fancy. It just has to do a job, and that's all it's there for. Like doesn't really have a radio in it. It's not painted nice. It's just a vehicle, just a tool. Okay, so what do we want to talk about next? I have chapter guides for the first chapter from pretty much everybody except for a few people who still didn't get a textbook until the last couple days. A lot of people, well, not a lot. Looks like 8 of the 34 people have submitted the second one. Most people have submitted the first lab. 29 of the 34. I need to grade 14 more of those. And then I have a couple people, 2 have submitted the second lab. Nobody's submitted the third lab yet. So we want to make sure that we're staying on all of that. And a few people have taken the first exam, 3 to be exact, and there's still like 9 days left before that one's due next Wednesday.
I noticed when we do our science labs, there's a few things in there that are missing that we have to buy.
What?
So I haven't started the second lab yet because I still don't have a metal spatula. And it's in a list, it's listed on the things I need. And the first one I didn't have matches, and it's not in the box either.
I
Is
don't.
there anything on the third one that we're gonna need to purchase?
I don't think the matches. I just assumed people would have matches around, but I guess not. Sorry about that, Rianne.
No, I don't have any.
The scoop. I had one in my kit. How about you guys? Becca, Shane?
Yeah.
You have a metal spatula?
Yeah. I mean, it's one side looks like a spoon and the other side looks like a scraper.
No, I didn't see that one.
Huh.
Yeah, I don't know. I'll have to go look at my science kit to see, but right now it's on the other side of the house from where I'm at. So
I bought personally one of those kits, and then that's how I got the labs. That's how I chose what stuff to use for the labs, because I assumed that everybody's kits were identical. So if you didn't have something, then that was just an error on the company that made the kits, and I'm sorry about that. But I don't. I'm writing them knowing what's supposed to be in all of those kits, except I mean I make some assumptions that some people will have this, like the matches or other normal household items. So everything should be there.
You
okay.
Okay, does anybody have anything in particular they want to talk about? Nothing?
Not really.
Okay. So we can probably start talking about chapter 3 stuff, because we're in the 3rd week. And this one is really like the biggest, most important chapter as far as what's going on with the planet and global climate change. And I think one of the biggest issues is people understanding what's happening and how temperature change can be a thing. And let's see, I have a picture here. Let's see right there. All right, not that one. Huh, where'd it go? Why is that dark? I'm gonna open that in Paint. That's okay. Let's make that big. Zoom, 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 zoom. Okay. And then I'll share that. Okay, can you guys see this picture?
Yep.
Yeah.
All right, so last week we talked about radiation and how there's a spectrum of radiation. The weakest rays are the ones that are radio waves, and then we move up into shorter radio waves, and then we move into microwaves, and then infrared, then visible spectrum, then ultraviolet, X-rays, and then gamma rays. And as we cross through that, so the microwaves and the stuff to the right of the microwaves are the not very much energy, and then everything on the other side of the visible range is dangerous to us. So what we need to make sure that we understand is that the visible light is sort of the, well, it's not sort of, it is the spot on the electromagnetic spectrum where everything changes, where we go from stuff that can't cause cancer to stuff that can cause cancer. And it's, if I'm looking at the rainbow, it's Roy G. Biv, red, orange, green, yellow, blue, violet. And so this side over here on the left would be your violet side. And so then the next thing is ultraviolet. Like this side of the visible spectrum or the rainbow is red, and this side over here is infrared. So the important thing to realize that happens with molecules and how things get heated up is when, okay, let's back a sec. Are you guys familiar with what the actual definition for temperature is? Think that is a no. So temperature is the kinetic energy. And I'm gonna draw a little line here. I guess I can just draw a line. That's a really fat line, but that's fine. Okay, so temperature is a measure of the average kinetic energy. And this line over the top of the kinetic energy, that's telling you the average kinetic energy. So the equation for kinetic energy is equal to 2. So let's do this. Let's in here. No, that wasn't good enough. Nope, that's not good enough. Nope. There we go. Dang it, and that's all over there. All right, so let's put that there. Okay, so okay, so kinetic energy is the energy of motion, and the equation is 1/2 the mass times the velocity squared. So if you put a thermometer in something, you're not necessarily measuring the mass because that's not really going to change, and the half is just a constant. So what you're really measuring is the velocity or the speed of the molecules. So the faster the molecules go, the greater the kinetic energy, and therefore when you're measuring that, it's the greater the temperature. So I want us to think about a thermometer for a second. So if I've got, let's see if I can draw one of those easy. How about using this one? Yeah, that works. And then I'll do a little paintbrush action here, maybe with this guy. Put a little red inside there. Okay, so if this is our thermometer and it's filled with red dye colored ethanol, when atoms or molecules like, I don't know, water or nitrogen or oxygen or anything like that touch it, let's maybe that one. All right, so let's say here's a molecule, and when that molecule is flying through the air and it hits the thermometer, so the molecules that compose the glass of the thermometer get vibrated, and then that vibration causes this alcohol in here to vibrate, and when things vibrate more, they'll expand. So what you end up having is a bunch of different collisions, and those collisions end up causing things to speed up, and when stuff speeds up, in general, things expand. So you'll end up with the thermometer rising, and it's all based off of stuff running into other stuff. Okay, so when I have something with an increased temperature, that molecule itself is moving more than something that has a lower temperature. So it's sort of like you have a cue ball that comes in and smacks the other pool balls and sends the pool balls off careening across the pool table. So how this works with light is, let's just use IR, because IR is the light associated with heat. So when infrared radiation hits a molecule, the molecule actually, the bonds between the atoms will actually expand, and then they're still connected to each other, so they'll contract back. And so what you end up with is like this rubber band effect where the actual molecules are vibrating away from each other, and you end up making the molecules themselves within themselves be moving faster. So since they're now moving faster, that means their kinetic energy is greater, and so that means their temperature is greater. And so infrared radiation is really good at making this bond bounce in and out. When we move down the spectrum a little bit, the microwave isn't quite as good at that. So what the microwave radiation can do is cause the actual molecule to start spinning in a circle, which is again making this molecule move faster. So when we think about the microwave, like the device that you have in your kitchen, what you're doing is you're causing the molecules to spin faster and faster and faster. And the microwave is a spectrum, just like visible light is a spectrum, and inside of visible light you've got all those different colors. Well, in the microwave, it isn't color related, but it's still dependent on its wavelengths. And there's a microwave length that is perfect for the water molecule, and it causes the water molecules to spin. And so if all of a sudden the water molecules are spinning in some pizza that you put into the microwave, then the water molecules are moving faster, and they bounce into like the cheese and the crust and the pepperoni, and then they impart their energy on that and make them go faster in the same way that cue ball hits those pool balls. And now everything is moving faster because the water molecules absorb some of the energy of the microwave. I'm sure some of you have like put a plate or a cup or a glass or something in the microwave, and you went to grab it and it was really hot. Like we have one set of green plates that we just don't even microwave anymore because the paint is also of the same rotational energy absorption for microwave, so the plate actually heats up a lot. So you don't want that. The best
ceramic.
Right, it totally depends on either the paint on the exterior of the ceramic, or if it's a particular type of ceramic material. The best things to put in microwaves are glass, clear glass. If you put clear glass in there, that won't heat up nearly as much as any of the other dishes you can put in there. So you're simply increasing the basically spinning of the water molecules, causing everything else to move faster. Infrared ends up doing the same kind of thing, except instead of spinning it, it makes it like slinky in and out. And both of those things, all that they're doing is causing the molecules to move faster. The big difference between what's happening on this side of the radiation spectrum and this side of the radiation spectrum is once I get to ultraviolet, When the ultraviolet hits this molecule, it actually separates the atoms from each other. It breaks bonds. And that's the scary thing. So we talked a little bit about this last week, but I'm going to put this up here anyway. Let's go here. I think it's here. And then, yeah, that's fine. Let's do this one. And then I'll share that. So this is DNA. It's a double helical, 2 strands. So I've got one strand going one direction. I got the other strand going the other direction. And they're connected up between each other by having an interaction on one of the strands interacting with another atom on another on the other strand. So these dashed lines, they're not chemical bonds. They're well, they're called intermolecular forces, but what I want you to think about is they're kind of weak interactions. But in the same way that when Velcro attaches to itself, if just one Velcro fiber was hooked by one Velcro, the pokey side, that's really easy to break apart. But when you've got thousands of those, hundreds or thousands of those, that all of a sudden makes that Velcro very difficult to segregate unless you pull it just in the precise manner. So the same thing happens with your DNA. The issue is with cancer is if, I don't know if I can draw on this. It doesn't look like it. This purple one right here, if this bond right here breaks, or one of these bonds over here where this P and 4 O's are breaks, this whole thing could get chipped out and something else can get put in. And once that happens, that DNA has been modified, and that will probably cause the cell to die. And that sounds terrible, but worse than the cell dying is the cell not dying and basically turning into a zombie cell. And that's really what cancer is. It just grows and grows and grows and grows until it infects everything else and then kills the body. So the main difference between what's happening with the spectrum of the radiation that's on this side over here of visible light, or IR and microwave R, and ultraviolet, is you break a bond. And when that bond breaks, then you can cause cancer. So last week we talked about ozone being able to block that UV, and so without that ozone layer, we would be in severe trouble. But that's not what we're talking about this week. This week is all about the stuff that happens over here. But really, this stuff right here. So most of the radiation that's on the planet, that comes to the planet, is in the form of this infrared radiation. And when we think about infrared radiation, what I want you to think about is you turn your stovetop on and your burner turns red and there's heat coming off of it. That is IR radiation. There's other radiation there. Obviously, there's visible light because you can see it and it's red. But most of the radiation coming off that particular piece of equipment is done has the ability to generate infrared radiation. And so that infrared radiation simply causes the molecules to vibrate faster. But it's not going to cause cancer because it's not actually able to break those bonds. When the sunlight comes into the planet, air particles, air molecules will absorb that radiation and they'll move faster, which is really important because we need this planet to not be absolute zero. We need this planet to not be the temperature that that space is. So we have this blanket of atmosphere over here, and those molecules are absorbing energy from the sun. So if you looked at page 109, figure 3.2, you'll see the sun transmitting radiation to the planet, and the planet absorbing some, reflecting some, and there's a very good balance with that. So you want to be able to absorb just the right amount and reflect just the right amount. About a quarter of the radiation that hits Earth reflects off of it. You can see that in other celestial bodies, like the moon doesn't absorb all the energy that the sun sends to it because you can see it. So that means the moon doesn't generate its own light. So the sun's sending its light to the moon and it hits it and reflects back down to us and we can see it. And the same thing happens with Jupiter and Venus and Mars and whatnot. If you've got a telescope or you know where to look, you can see Venus maybe in about an hour, and then again early in the morning, because the sun's lights or radiation is reflecting off of that. Well, what happens if not as much radiation reflects off of it? So we're expecting, say, 25% of all the atmospheric radiation to reflect off of the Earth, or a bunch of the stuff that's absorbed is re-emitted. So if 25% gets reflected from the Earth and about half of it gets absorbed by the Earth, well, we need to make sure, what also happens is some of that reflects out. Well, what if less of it reflects out? What if less of it actually leaves the planet? What if the radiation that made it to the surface of the planet doesn't leave? Because some of it needs to leave. That's we're at an equilibrium where some leaves and everybody's okay with that. So what happens if less of it leaves?
Stuff gets hotter.
The whole planet gets warmer. Is that a problem? Yes, that's a huge problem. It's a huge problem because we're all, and by saying we, I am meaning every living organism on this planet, expects the planet to be at a certain temperature. And when certain temperature isn't maintained, then things simply die. I think we talked, oh, maybe that wasn't this class, but maybe it was. Does anybody remember me talking about why I'm not worried about getting a flu from my dog?
Yeah, the animal has a different temp than you.
Yeah, the animal has a different temp than me. It's warmer than me, so those microbes can't live inside of my cold 98.6 body when they're super happy in a 102-degree poodle body. So if all of a sudden the temp went up a couple of degrees, we would have some viruses that would be super happy and some of them that would just die. What virus kills more people on this planet than any other?
The flu.
Nope.
Well,
Nope. Something with a scarier name than the flu. I'm talking about this particular virus because we're discussing things that would happen to the planet if the planet got warmer. So what's something in an area where it's warmer that people are worried about getting? No? How about, maybe I shouldn't have said a virus. I'm sorry, it's not actually a virus. I should be saying a microbe, but it's a parasite. Is that better?
not clear on it, but is it malaria?
Yeah, yeah, nailed it. Malaria kills more people than anything else. And we've got like tens of thousands of cases in the US every year, and we're not even in the temperature range that the malaria likes. Somewhere between 10 and 30,000 US cases, but worldwide, hundreds of thousands of people die of that. It's actually Bill Gates, one of his top 3 things that he's trying to stop. So just like some people in the 50s were trying to stop polio, Bill Gates is trying to stop malaria from killing so many people. So if the planet got warmer and our area here in the Pacific Northwest turned into an area where malaria would be more comfortable because it would be warmer and probably wetter because the ocean is right there, then we would be exposed to malaria all the time, and it would be difficult for us to handle it. There are lots of good malaria meds, but they're mostly for people who don't live where the malaria is. They're for someone who's going to go to a malaria area and it keeps them from getting malaria, and then they leave and they stop taking the meds, and then they don't have to worry about it anymore because they're not going to get malaria at their home. But we're working on that. So if we're producing a bunch of molecules that have the ability to absorb this infrared radiation from the sun and hold on to it in a vibrational state, that's going to cause the planet's temp to go up. So what you end up having is the sun, let me come up with a better drawing here now. How about where did that go? Sorry, I lost it. I have to pull it back up. Save image. Yeah, I don't want to work. Okay, you guys seeing this bad picture of the sun and the earth? Actually, I don't really want to show that one too because I need to edit it. So let me kill that and then open this in Paint. And go to desktop. Go there. That's it. Alrighty. So so you can see lots of stuff's happening here. So the sunlight's coming down and some of it gets reflected off here. Some of it gets scattered by the upper atmosphere or absorbed by the upper atmosphere. Clouds do a good job of absorbing that energy, so then that cloud will end up having more energy. And like I said earlier, about half of it makes the Earth's surface, and then some of it gets reflected back. So as it's getting reflected back, so here are these clouds. They absorbed energy, and they're also reflective. So if I change the gases that are in the atmosphere here, those gases might absorb or not, might absorb more or less of that energy. So if I put like a bunch of carbon dioxide in the atmosphere, this 4% of the light that's supposed to be leaving the planet, 4 to 6%, gets absorbed by that carbon dioxide. And now that carbon dioxide is moving faster, so its temperature is higher. So all of the molecules on the planet's average kinetic energy have increased. So thereby we've increased the temperature of the planet. So we keep pumping more and more of this stuff that's good at absorbing the light that's supposed to be reflected off of the Earth and keeps it here. So it would be like it's 70 degrees outside and you put on a big thick jacket, and then you put on a sweater over the top of that, and then you put on a sweatshirt over the top of that. You don't need it, you don't want it, but you keep doing it, and we keep doing this to ourselves. So we're insulating the planet better and better and better, and the planet doesn't need to be insulated better. It's been taking care of itself for quite a long time at this particular conditions, and it would be bad if we change them. And we are doing that.
Not just that, but along with that extra energy in the air, we're getting more energetic storms. It's like storms are getting worse. We're getting nastier winters because of it.
So this whole phenomenon of climate change started, do you guys know what it started off, people we were calling it when we were first concerned about it? It wasn't called climate change, it was called something else. Yeah, it was called global warming. And that's absolutely a problem, global warming. But there's more to it. So now we're calling it climate change because bad stuff's happening. So let's look at, I don't know, let's see, how about this one here? This one works. Just as an example. So I'll save this image, go to the desktop, and then use Paint again. Let's open that guy up. Go here. Don't save. Ooh, that's really small. That's fine. Share. Share. Okay, can you guys see this jet stream thing?
Yep.
All right, so because the planet is spinning and there's a fluid on top of the planet, you end up having wind generated. And so there's a general pattern for how the wind makes it around the planet, and we call that thing the jet stream. So the air typically comes off the Pacific Ocean, crosses over Oregon, then does this sine wave kind of situation through the Midwest and then out up through the upper Northeast. So, let's say you were driving your car and the speed limit around a particular corner was 20 miles an hour, but you were driving 50 miles an hour. Are you gonna hold that corner well?
No.
Might you go outside of your lane onto the berm a little bit just so you can make that corner? So what ends up happening is this airspeed ends up being faster because the a reason that the jet stream gets created is you've got warm air on the surface of the planet that rises. Well, if the air on the surface of the planet is warmer than you would expect it to be, the air rises faster than you would expect it to be, and then this air is moving faster than you would expect it to be moving. So if this air is moving faster, let's see if I can find a better one. Then when it goes to try to make the corner, it doesn't quite make the corner as well. So it got further up. So tell me, because the jet stream crossed further north, what's going to happen to Nebraska here? The air, instead of going through Oregon, Washington, Idaho, and Montana and hitting that, it went up way up into Canada. So tell me about poor Nebraska. Nobody wants to hazard that guess. It's going to get a lot colder because this air went up to a much colder region. Well, what if it got up to a much higher latitude? Then it would be much, much colder down here. So the phenomenon that's been happening in the last 4 to 5 years is called the polar vortex, and that's caused by the jet stream doing things that it's not supposed to do, which is getting further and further away from its traditional going through Oregon, Washington, Idaho, and then coming back down and ended up into the south and then coming back out the northeast. The jet stream itself is not taking its corners well. It's getting outside of its traditional lanes. There were some people who died in Mississippi this week. Mississippi, Georgia, Alabama, Mississippi this week because a tornado was generated. They've never seen a tornado this time of year in that state. And it's all caused by these increased temperatures causing air to move faster than it's supposed to be moving. When Katrina hit, that was the biggest hurricane we'd ever seen. Now we've seen 3 bigger than that since the Katrina hurricane. So why is all this happening? Because the planet is absorbing more energy than it's supposed to be absorbing, and so it causes air particles to move in ways they're not supposed to. Also, when the 2/3 of the planet is covered in water, when you've got an excess amount of radiation being absorbed by that water, then that water tends to turn into a gas and ends up in the atmosphere. So you've got more moisture in the atmosphere than you're supposed to. And when that kind of thing happens, you get the Midwest here completely covered in water. And then you get, I can't remember if we talked about this in this class or not, but millions of calves dying. Did we talk about that?
You mentioned it.
What's going to happen to the price of beef?
Skyrocket.
It's going to skyrocket, and that's going to happen in 2 years when those calves are supposed to be slaughtered, and they're not here because they died in that flooding in the Midwest. Okay. What else do we want to talk with this? So those are some phenomena. And now in chapter 3, it talks a significant about how molecules arrange themselves. And the arrangement of the molecules might not seem very important, but it turns out to be monumentally important to how certain molecules will interact with other molecules. So let me get out of this. Let me open up that. Let's see if this one. All right, let's talk a little bit about bonding, and then we'll go on to shapes. we'll do this one here. All right. So first set of the first chapter talked about being able to name molecules that were covalent, and it talked about the second chapter talked about single bonds and double bonds and triple bonds. And you get the same kind of discussion or a little bit of this in this chapter in 3.3, and it wants to talk about the location of the atoms relative to each other, their bonding, and then how that relates to their positions. So before we do that, let's talk a little bit about covalent bonding. So when molecules covalently bond, it's because they're sharing electrons. So the Lewis structure for the fluorine atom is 7 electrons, and you know that because it's in the second to last column on the periodic table. So that means it's got 7 exterior electrons, and what these atoms are trying to do is get an 8th electron. They're trying to look similar to the noble gases, because once they do, then they can stop reacting. Stuff that wants to react doesn't act like a noble gas. So what they try to do is they try to react until they don't want to react anymore. So if a fluorine atom got 1 more electron in its exterior, then it would have the same kind of electron structure that the neon atom does. And so fluorine is basically trying to look like neon. So the way the fluorine atom does that with another fluorine atom is each one of those atoms donates 1 electron to form a bond, and when that does that, then I get these 2 electrons here shared between the 2 atoms, and that's a covalent bond, and we're going to call that a single bond. So a single covalent bond is the sharing of 2 electrons, and these 2 electrons here can be replaced by just a straight line between the 2 of them. We need to talk about electron configuration, so we'll skip down. So oxygen is right next to fluorine, and when you move over 1 spot on the periodic table to the left, whatever atom you're talking about has 1 less electron on its exterior that is available to do stuff. So if you look at both of these oxygens, they have 6 electrons on them. And so that's 2 away from 8. So what ends up happening is each of the oxygens donates 2 electrons to the other oxygen. So they're sharing 2 apiece. So that's 4 total electrons being shared. Each one of those pairs is a bond, and so with the oxygen atoms, the O2 that you're breathing right now is actually doubly connected to itself. So there are two bonds holding those 2 oxygens together. Now if we move over to the nitrogen has a triple bond on it. All right, so the fluorine is a single bond, the oxygen will have a double bond, and the nitrogen will have a triple bond. And the reason for the triple bond, the reason that it's needed is we've got 5 electrons for nitrogen. You know it's 5 because nitrogen is, again, 1 to the left of oxygen. So that means it has 1 less electron in its exterior. So we end up needing to have 3 electrons to get itself up to 8. So like this black nitrogen here, it sees its black 5 electrons, and then it sees these 3 electrons from the other nitrogen that are red. So it kind of sees 8. And then we can do the same thing on the other side, these 5 red electrons for the nitrogen, and then these 3 black ones, and then this nitrogen kind of sees 8. And so that ends up forming a triple bond. Fluorine is phenomenally reactive. And the fluorine atom would much prefer to just steal an electron from another atom, but it can't steal it from another fluorine because they both have the same amount of strength. So this is a very reactive substance. Oxygen is also reactive, but it's not even close to being as reactive as fluorine. And a lot of that has to do with the fact that when this needs to react, I have to break both of these bonds before the oxygens can go off and do something. And it's always a lot harder to break 2 bonds than it is to break 1 bond. So what do you think happens with the nitrogen and its ability to react? Anybody? If you follow that trend, the fluorine is,
It would be even harder.
yeah, it's going to be a lot harder. So it's significantly harder. It's so much harder that the N2 molecule itself is almost as unreactive as a noble gas. It doesn't do anything when nitrogen is involved in a situation where there's a fire happening. It just passes around the fire through the fire and nothing happens to it at all because those guys are so monumentally connected to each other. That's kind of problematic because plants need nitrogen. They have to have nitrogen and they can't use it in its N2 form. So it's kind of, I mean, it's sort of like the way it's sort of sad for us as humans that we have all of this sugar around us. You look outside and you see all those trees and grasses and bushes and leaves and branches, and that's glucose. But you can't eat it, even though you can use glucose because you can't disassemble the molecule. And the same thing is with the plants. The plants want nitrogen, and they're completely surrounded by the nitrogen in the atmosphere, but they can't use it. So since they have to have it, and the plants themselves can't get the nitrogen off to separate out so they can use it, does anybody know how the plants actually get the nitrogen to make it usable? Take that as a no. There's two methods. There's a bacteria that can live on the upper portion of the roots of plants, and that bacteria has a little protein molecule that can break the nitrogen in half. So start the N2 molecule in half, and then you'll have an N and another N that'll probably attach to an O2 and then end up turning into like a nitrite or a nitrate that the plant can use. So the bacteria and the plant form a nice symbiotic relationship. The plant gives the bacteria a place to live, and the bacteria pees on the plant, producing, and its pee is a fertilizer. The other method is when lightning travels through the atmosphere, it can break all the bonds as it's traveling down through the atmosphere. When that happens, the O2s get broken apart and the N2s get broken apart. So if this nitrogen is off by itself, and it runs into an O2, they'll make a molecule together. And then that will get trapped in the rain because there's usually water in, it's usually raining when there's a lightning storm. And then that ends up in the soil. So places where there are lots of lightning, the soil itself is very rich. Where in the planet or where in the country is there lots and lots of lightning? How about in the United States?
Yes.
The Midwest is covered with lightning, right? It happens every summer, every late spring, every late fall, lots and lots of lightning. Tornadoes come along with that stuff, but the tornadoes obviously are devastating, but you get all that lightning and then you get a bunch of fertile soil. So that Midwest is the breadbasket because it can produce a bunch of wheat and corn because the soil is so fertile.
And then we get to crops in our areas and all that, and there's a reason why we have crop rotations.
Yep, absolutely. So some of those plants actually put nitrogen back into the soil. Things like rapeseed and mustard seed, certain kind of beans will put nitrogen back into the soil. And so if you're having a problem with your garden and maybe you've been gardening there for a few years and it's not producing the way it used to, you could crop rotate. And the nice thing about the crop rotation is usually you can pick ones that grow during off seasons, like after you've harvested your garden and before you've planted your garden, and then they can replenish the nitrogen. But if it's been a while since you've done that, you might actually need to spend an entire year where you're growing alfalfa to make sure that there's enough nitrogen in the soil. People figured that out quite a long time ago, mostly by accident, but usually a farm will have sections where they're not growing anything that they can sell for a lot of money, just a little bit of money. Usually ends up being something like alfalfa because you can sell that for feed for livestock. So these three molecules are really easy to see what their shape is, and their shape, since there's just two things there, they're just connected to each other, so it's in a straight line, so it's called linear. So all three of these are just linear. But what happens when I put a third thing onto a molecule and have them all hook up together? Let me scroll way down here. All right, so if I've got something in the middle and two things are connected to it, but I want to get them as far away from each other as possible, the structure to do that is a linear structure. So let's say that that you've got, I don't know, some 4-year-old boys and they're like punching each other and they're kicking each other and they're fighting. and you go over and you pick them both up by the backs of their shirts, what do you do with them? Do you like you put them right out in front of you so they can reach each other? No, you separate them. And that's how I want you to think about electrons. All atoms have electrons around them. So if I've got a centralized atom and it has two atoms connected to it, then those atoms have electrons around it. So the best thing to do is get those atoms as far away from each other as possible. And so 180 is the structure that that's going to look like. So if we scroll way back up here, actually we can just go to right here. So here's a carbon dioxide molecule. It's got 3 atoms on it. Carbon's in the middle, oxygen's on both sides. This molecular shape is linear because if I'm a central atom and I've got 2 things connected to me and I want to get them as far away from each other as possible, I just put them 180 degrees away from each other. But what happens if I've got 3 things connected? So if I've got 3 things around the center of something and I need to get those things as far away from each other as possible, I put them in a triangle shape. And so those things are going to be 120 degrees away from each other, and they're as far away from each other as possible. And a molecule that would look like that would be something like aluminum chloride. So this aluminum atom's got 3 chlorines around them, and I get them as far away from each other as possible because you can see these chlorines have all of these electrons around the outside. And those electrons are all negative, and so they all want to be as far away from other atoms that have electrons around them. So what happens if I add a 4th thing? So this is a flat 2-dimensional structure, and this is a flat 2-dimensional structure. But the moment I put 4 objects on, the structure needs to be 3D. And if I don't make it 3D, then if I put a 4th thing on here, this would just be a box, and they'd only be 90 degrees away from each other, kind of like we see here. This would be a box in the middle, and they're only 90 degrees away. But here, I can get them further away if I actually end up forming a tetrahedral. So that tetrahedral allows me to get 4 things further and further away from what they are. And so this would be like the methane molecule, where there'd be a carbon in the middle and hydrogens around the exterior. I don't know if we need to talk about stuff that's bigger than that. Probably not. We need to talk about some exceptions, though, where sometimes what we're looking at, we're not... there are other factors besides just atoms that can cause the molecule to be in a different shape. So there's the methane molecule. So there's how you might write it down, or might see it drawn in a book. And then here's 2 other ways you can show it with the perspective model and then the ball and stick model. So let's do... All right. Let's look at these guys down here. So let's say that we'll start over with this one again. If I've got an atom and around it, it's got 3 other atoms, then the shape is going to be this traditional trigonal planar, meaning I've got a triangle shape and everybody's 120 degrees away. But what if the molecule I'm looking at, instead of having 3 atoms on it, it's got 2 atoms on it and then a lone pair of electrons? If I'm looking at the structure of the molecule, this one looks like a triangle. So it's called trigonal planar, but this one doesn't look like a triangle. It's bent. The reason it's bent is because this atom right here actually has extra electrons on it, and those electrons are pushing just as hard as these electrons around these atoms. And so you end up having a situation where the electrons on the central atom cause the shape to be different. So instead of this being a linear structure, which is what you would expect for an atom that has 2 atoms around it, the structure ends up being... and the NEM's not really complicated. It's just the molecule is bent. The next example I can give you is for tetrahedral. So we'll just talk about the 2 options with tetrahedral. So if all 4 of the atoms around the central atom, or all 4 of the things around the central atom are actual atoms, then I'm going to say that's a tetrahedral shape. But if one of those things is just a lone pair of electrons, then I end up having something called a trigonal pyramid. It's a trigonal pyramid instead of just a pyramid, because pyramids have 4 sides and this object only has 3 sides on it. And this one's really important because this is the shape of ammonia, where the central atom would be a nitrogen, and then the other atoms around it are hydrogens, and you probably know ammonia from, say, Windex. And then the last example for what we're going to be talking about today is another bent structure, and it's bent this time because two of the spots where I'd expect atoms to be have lone pairs of electrons. So this one might look super complicated to you, but it's actually, and it is kind of complicated, but it's incredibly important to us because this is what the water molecule looks like. The water molecule is an actual bent molecule, and the reason it's bent is because if I look, let's pull up Lewis structures. Lewis. So the dot diagram for oxygen has 6 electrons around it. You can see in this picture here, there are these 2 electrons and these 2 electrons, and then these single electrons. And oxygen likes to make 2 bonds, and when it makes 2 bonds, you can, like, this guy's wrong, it's only got 1 bond, it needs actual 2 bonds. And so this is the structure. You end up with a structure that looks like this, where there's 2 electrons in between, and then I still have these lone pairs of electrons on the exterior. But let's add this to water. For water, you end up with this structure here. So this is a tetrahedral shape. That's because there's a lone pair of electrons here, a lone pair here, and an oxygen or a hydrogen and a hydrogen. And that forms that tetrahedral, but when I talk about the shape of the molecule, I only talk about the atoms. So I end up with a bent structure. And this turns out to be incredibly important because this is what makes water polar. And the polarity allows water to mix with other things that are polar, like ammonia. When you've got things that are nonpolar, they cannot mix with the water molecules. And so the structure, the shape of the actual molecule turns out to be monumentally important. It talks about that in section 3.3 in the text. All right. Do you guys have any questions about molecular shapes? In this water molecule, how did you, or say this one is probably a little easier, how do we know that this is the number of dots we're supposed to have? You can look on the periodic table, and when you do, you'll find oxygen that's in the column that would give you 6 dots around it. And you know it's 6 dots because it's 2 away from the last column, the noble gas column. And so that means it's looking for 2 more electrons. And the Lewis dot structure for hydrogen is just an H with 1 dot. So when those H's come in, each of the hydrogens show up with 1 electron. And when they show up with 1 electron, you end up having one of these electrons is the hydrogen electron, and the other one is from the oxygen, and then there's 2, 3, 4, 5, 6, 7, 8 total electrons, and now that oxygen is happy because it sees 8 electrons. And you end up with that structure there. And so it's got that bent nature to it, making the water molecule pulled.
Is there any exceptions to the 8 electron rule thing?
Yep, there are 3 easy exceptions. Anything that's in the boron column actually only wants to see 6 electrons. And if you're talking about sulfur and phosphorus, both of those atoms have the ability to have more than 8 electrons. So if I look at something like the sulfate polyatomic ion or the phosphate polyatomic ion, so here's sulfate. Each one of these lines is a covalent bond, and each one of these lines, each covalent bond is representing 2 electrons. So there's 2, 4, 6, 8, 10, 12 electrons around this sulfur. So that sulfur is seeing 12 electrons instead of seeing 8 electrons. And the same situation happens with phosphorus. So here's a phosphate ion, and this phosphorus is seeing 1, 2, 3, 4, 5 bonds around it. So that's 2 per bond. So the phosphorus atom is actually able to see 10 total electrons. It doesn't have to, and it'll only do it if it has to do it, but it can do it, both the phosphorus and the sulfur. So if you're trying to figure out shapes and how many electrons you have around different atoms, you would need to assume it was 8, and then if it wasn't working out for you, then you'd end up just tacking on more bonds to the phosphorus or the sulfur until everybody else was okay. Because if you look at this example with the phosphorus, count the electrons around that top oxygen. There's 2, 4, and 6, and then that bond is 2 more electrons, so there's 8. The one on the right and the one on the left are the same situation. They're also seeing 8. The one on the bottom has 2 electrons on each side, and then 2 sets of electrons in each one of those bonds, so that's another 8. So all the oxygens are happy seeing 8 electrons, but the phosphorus sees 10, and it's okay. It accepts the fact that it needs to accept more electrons. Did that answer your question, Shane?
It does.
Okay. Aurelia or Becca, you guys have questions?
No, I don't think so.
Okay.
No, no.
All right. Okay. Well, well, you guys didn't tell me I wasn't sharing that. Dang it. I was going through all that stuff and you couldn't even see it. So there's that phosphorus or that phosphate, and the top left and right, all of those oxygens are seeing 8. And the bottom one is also seeing 8, just in a different way. And then that phosphorus has 2, 4, 6, 8, 10 electrons around it because it's got 5 bonds, and each bond is 2 electrons. And let's do that. Not that one. And then there's the sulfate. And so that sulfur is seeing 2, 4, 6, 8, 10, 12 electrons. But then each of the oxygens are seeing 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So it's happy. And the sulfur is just sort of taking one for the team, absorbing all those extra electrons. Okay. I think that's probably all I got for today. If you guys have any questions, I'll answer them. Okay. All right, I'll take that as a no, and thanks for showing, and I'll see you guys online or talk to you guys on Wednesday.
Okay.
All right.
Ready?
Bye-bye.